Let's get started. So in today's practical session, what we will do is to build a CNN architecture to do image classification tasks to differentiate cats and dogs images. Okay, so the package or the libraries that we'll be using is TensorFlow Keras in Python. The dataset that we will be using is the one that we have already looked at last week. That is the cats and dogs. So this is a link in case you haven't downloaded and uploaded to your Google Drive yet, please do so that you can run the Colab notebook. Okay, so on what we will be discussing today, how to build this network, the code is already provided to you in this Colab notebook. What you need to do is just to save a copy to your drive, and then you can do some modification and experimentation at home after this session. Okay, so in this session, what I will do is to go through the entire process with you so that you know clearly what each line of code is about. Okay, and what can you modify based on the based on the template that I have already given to you. Okay, so this is for today's class. It should take roughly 40 to 50 minutes to complete the explanation. Yeah. So we want to start by introducing to you the TensorFlow library. So TensorFlow library is so far the most useful library whenever we are working on deep learning or neural network based model. Yeah. So this TensorFlow is open source, and this is the API that is sitting within TensorFlow. So within here, we can see that we have TensorFlow Keras, we have estimator. Estimator are all the models. Yeah. We have the neural network architecture that is predefined here. We have all the loss function. Loss function is a way to compute the error. We have also matrices. Matrices are ways or algorithm that we use to compute the accuracy, precision, recall, F1 scores. Optimizers defines the learning rate. How do we want this neural network to learn from our training model? Do we want it to learn fast, or do we want to take a stepwise learning approach? So all of these are optimizers, and the rest of them are not so helpful unless you want to do very, very advanced deep learning based project. So now this TensorFlow is a very comprehensive library for all the neural network, all the resources that we require to build neural network. And there is actually another more user-friendly way of coding them out, which is Keras. So we will be using Keras to use the resources that is sitting within TensorFlow. Yeah. So what is Keras? Keras is a high-level API for TensorFlow. So what it does here is it sits on top of all the TensorFlow resources, which involve all the algorithm, the lower-level API, as well as the hardware that TensorFlow is running on. Okay. So we will be using Keras. We will be using the relatively simpler codes to build our neural network. These are the documentation that is related to Keras. Yeah. And because we will be using a very high level API, which means we have to follow a certain way of working, which is relevant to Keras process flow when it comes to building our neural network. So if you remember in our lecture, what we mentioned is a neural network can consist of multiple layers where we can stack this convolution neural network, max pooling, and other neural network to build one whole entire architecture. So this is what we will be looking at today. Yeah. So in order to get started, we have to follow this workflow. Yeah. It is not like how we build a machine learning algorithm where we just need a simple line of code to say like, hey, build this linear regression, and that's all. We fit our training data to that algorithm. So now for neural network, we will have to define the network because there is a lot of flexibility for us to build totally different architecture from one person to another. Yeah, so this is just an example. So how many layers we want to extract the features? How many layers do we want to learn from our features to produce a prediction? Yeah. So now, these are the 5 steps that it takes. So the first step here is to define the network. So defining the network means how do we want to stack these layers? So do we want this convolution to follow another max pooling? How many convolution layers do we want to extract the features? So this is our design. And the design step is called defining the network. So now, after we define the whole entire architecture, so now we then have a network architecture that is that we suppose it will help us learn the features, yeah, extract features and learn the feature to make prediction. So now, how do we want this architecture to learn from our data set? It's a step called compiling the network. So in terms of compiling a network, we want to specify a learning method for this neural network. Say, for example, we want this architecture to learn fast or to learn slow. That is under optimizer. So now the model, this architecture, again, when it runs the code behind, it will also generate some metrics. So say, for example, for each steps that it learns from our training data, what is the error that it makes? So those errors are some algorithms that is saved under the loss function. So each loss function has its way of calculating what error is. But at a very high level, what we need to know is loss function represents the error which the model is making for each steps. So matrices defines how well a model is doing its task. Usually we use the accuracy as the metrics. Yeah, so that is on compiling the network. So once we have the architecture as well as the learning style that we want this network to learn, we can then fit the network. Fit a network means we put our training data set to this architecture and get this architecture to learn from our images. That is on fitting the network. So then after we fit this network, what it is trying to do is to learn the weights. To learn the weights for feature extraction, as well as to learn the weights for prediction. Yeah, if you still remember, what it is trying to do is to learn all these weights of the filter for each steps of training. Yeah, it is going to compute all these values as weights. Okay, so once we have all the weights, we will then be able to use the trained model to make prediction. And before it comes to making prediction, we also want to evaluate the network to see if it is overtraining, overfitting, or it is training just nice. It is not overfitting. Yeah, so that is the 5 steps that it takes for building a CNN-based image classifier. So then we want to start with defining the network. And before we come to this defining the network, we'll just do a recap on what we covered last week. Okay, so what we covered last week. The first step to work with our image data or image classification is always to mount to our drive to connect our notebook to our image data. So we will be mounting our drive and also to define all the paths, right? So after defining the path, what we need to do is to load the images and augment the images, right? So in terms of augmentation, last week, what we have looked at is how to use this image data generator to operate on our data. So do bear in mind that whatever which we discuss in augmenting the data only apply to our training data. Should only apply to our training data. Yeah, and we shouldn't apply the same data augmentation operation on our validation and test data set. Okay, understand why? Do you know why we shouldn't augment the training and validation data set? Huh? Okay, so why do we not perform the data augmentation on training and validation data? Huh? Yeah. So there's just no point of augmenting it. The point of data augmentation is at the point we want to train the model to see more representation. And when we don't use the image for training purpose, we just don't have to augment them. Yeah, we save our resources on evaluation. Okay, so if let's say we are not doing any data augmentation on the training and validation data set, what we need to do now on the training and validation data is to rescale them. So rescaling is an operation that has to be done on all the images that is used for training or validation or test purposes, because neural network reads a value from 0 to 1 more efficiently than reading the values from 0 to 255. Okay. So now we also need another function image for loading our data in batch, which only involve a rescaling function. Yeah. So once we have defined this training and also the testing operations, we will then apply them to flow all our data from the training and also from the validation images or folders. Okay. So once we have all the data ready, we are then all set for CNN modeling. So the first step to CNN modeling is defining the network. So in the lecture, we mentioned that this image classification neural network is a step-by-step architecture. So under this TensorFlow Keras, there are two types of APIs. First type of architecture is the sequential architecture API. Another type is functional API. So this sequential API allows us it provides a template for us to stack this layer by layer without any flexibility. So for every step that we define, the program will know that it is going to run one after another. So on the functional API is the one that we won't be touching on. So it allows more flexibility, like for example, recurring kind of architecture. Okay, so those are more advanced in a way. If you have the chance to learn generative modeling, then this one will be pretty helpful. Okay, so how do we go about defining them? In order to define this neural network, we will need definitely TensorFlow. And from the models template, we will import the sequential template. Yeah. And from the layers, we will be importing the convolution layer and the max pooling layer. Still remember what is this convolution layer and max pooling layer for? The function of convolution layer and the function of max pooling layer. Function of convolution layer is to extract features. Remember that? Extract features, correct? And the function of max pooling layer is to reduce the dimensionality, make the data smaller. Okay, so convolution layer extract the features, max pooling layer reduce the dimensionality, makes the feature smaller. Okay, but still maintain the spatial invariance. Yeah. So how are we going to start is, okay, we give a name to our model. Let's just say we give a name of model to this model. So once we define the model, we will then take sequential function from these models. these models. Okay. So once we define this, and the program will know that, okay, we are using this template to stack the following layer from one layer to another layer. So to define our first convolutional neural network, what it takes is, we'll just say, take this same model, add layers, a convolution layer, and what are the arguments in this convolution layer. Okay, so now we mentioned that we know that a convolution layer or operation consists of multiple things, right? So now this is supposed to be helping us with extracting the features, right? And we sort of, if you still remember this slide, we talk about how many features are there to help us identify the X in this format and in this format. So in this case, there are three main features that can define X, right? It is the middle where the points cross. And then there is this edge, which is from this direction. And there's this edge, which is from this direction. So as long as we have these three, it should be sufficient to define whether the picture is an X or not. But right now here, what we are trying to do is, we are trying to extract the features of cats and dogs. And therefore, we may need more filters compared to just three of them. Yeah. So the first argument here defines the number of filters do we want for this program or this neural network to identify or differentiate cats and dogs. We are saying that, okay, there should be around 33 differences, 33 features. So now it is trying to learn 33 features. Okay. So then the next argument here is the size of the filters. So what is the size of the filter? So in the example that we have seen in lecture is a size of 3 by 3. Let's just say we want also a 3 by 3 filter. Activation function is to introduce nonlinearity. Therefore, we use a ReLU function. And the input shape is the shape of our image, which is the one that we specify as and in the step where we bring in our data. So this have to tie with this value here. So 150 by 150 is the dimension, and this 3 indicates that it is an image, colored image, okay, RGB image. So this is how we define the first layer of our CNN. Okay, so it's a convolution layer. So now, say for example, we want to stack a max pooling layer following the convolution layer. So what we do here is input a max pooling layer, and we define the size of the filter. Okay. And what is the stress? Stress of 2 means how many steps do we want to take as it slides across our image. Okay. Say stress of 2 means every time it slides over the image, it will jump 2 pixels. So this is a stress of 1. In the case of stress of 2, that means first time it will be here. On the next step, it will jump to this position instead of this position. Okay, that is stress of 2. So that's how we construct our first convolution layer. So let's just say, for example, we want to stack on more and more convolution and also max pooling layer to extract the higher level features. So then we'll just keep on stacking this layer onto one after another. And what we can modify from here is the size of the feature map by max pooling, and also the number of features that we want to extract from each step, whether we can increase them or reduce them. Yeah. So we will always reduce the size of the feature map before increasing the number of filters that we try to learn to maintain sufficient efficiency. Okay. So that's how That's what it takes to build the feature extraction part. So now if you still remember, after the feature extraction architecture, we will be arriving at the predictive layer. Okay, so now what we have just defined right here are the convolution and also max pooling, convolution, max pooling. So what we are trying to do here is to stack the feature extraction layers to produce multiple feature maps. So now, in order to build this into an image classifier, we will then have to channel all the learned features towards the end to a fully connected neural network. So before we channel these features into the fully connected neural network, what we need to do is to put this 2D array into a 1D array called the flattened layer. Okay, so in order to do that, we will be adding a layer called flatten. So this layer tells us that, okay, so this is the end of feature extraction, and we are going to do something else. It's either object detection or image classification. Yeah. So once we flatten this into 1D array, we will then channel all these features into our dense neural network. So dense neural network here refers to the fully connected neural network. So in this case, we see that we are adding all the learned features to 1024 neurons to learn the features that is relevant to its specific class. And then we are trying to just output them directly after one layer of neural network. Yeah. So the first layer here refers to the input layer, and this layer here should be referring to this layer before it gives us our output. So now at the output layer, the number that is reflecting here should reflect the number of class that we are trying to predict. Yeah. So in this case, we are predicting cats and dogs, and therefore the number is 2. In the case where we are predicting 13 classes, this output would be 13. Yeah. And the activation function, the recommended activation function for the output layer is softmax. Okay. This softmax is applicable to multi-class predictor. So it is recommended to use this. Another famous one would be a sigmoid function, but sigmoid function only applies to binary class prediction. Yeah. So this is all. What we have just done is to define the neural network at this point of time. So what you can do at home is try to modify the stacking of each layer in terms of feature extraction, as well as the prediction layer. So over here, you can stack more and more layers so that it learns more feature that is relevant to the output. Over here, if you want to modify this, it means what you're trying to do is to modify the feature extraction layer. What feature are you learning? Okay, got it? That is all. So try to modify the layers and visualize the changes. Yeah. So before we go to compiling a network, let's just say it's very difficult to memorize what we just defined, right? And how do we check the architecture of the CNN that we just built? So we will be using a .summary function to provide us the summary. So this is what it looks like as a summary of our neural network. So these are all the layers that we have defined. So remember, the shape of our input image is 150 by 150. And in this case, we can see that after the convolution layer, the size reduced to 148 by 148. Okay, why is that so? Yes, it is extracted. I hope you still remember the operation where we see that the size reduced after the convolution operation. So from this size and reduce to this size because we are sliding the filter across to extract the numbers. Okay. So in the case we want to maintain the size of the feature map, we have to apply additional padding to the image. Yeah. So now this 32 refers to the number of filters that we have learned. So it doesn't it shrinks the size of the feature map, but this remains. Yeah, we get 32 filters. So after max pooling, we have 32 filters. But right now, what does max pooling do? Reduce the dimension further, yeah, but still maintain the important features within this feature map. Yeah. So now after then we apply another convolution layer. And after another convolution layer, we can see that it reduced the size a little bit further, but we have mentioned that we wanted more features from the feature map, and therefore we see more feature map. So it is by this stacking, we can shrink the feature map and at the same time increase the number of feature maps to maintain certain efficiency of the entire architecture. Okay. So this is how it looks like. So we can see that all this feature extraction layer is trying to give us a 2D array. We are still maintaining how these pixels is related to each other before it comes to the prediction layer. So now, once we flatten the layer, what it means to us is we are trying to make this 2D array, this 7 by 7, into a flattened, into a 1D array. So we are combining all these features that we have extracted, 128 of them, into one single array. So this is the feature of a single image. So then we will be channeling all these features to our fully connected neural network to learn the pattern that is related to its class in order to give us the classification. Okay, so that's how it looks like. So there's also another type of illustration that we can plot. So we can use this plot model function to plot this one. It is similar to this output, except it is in flowchart format. And in this illustration, it involves the shape of the input and also output of each step. Say, for example, this one, the previous one doesn't tell us the input shape, right? And this one will tell us, okay, we input the image as a size of 150 by 150. We have 3 channels. And the output is also this size. And then after the first convolution layer, what we are trying to change is from 150 to 150 by 150 to 148 by 148, so far and so forth. Yeah. And that's about 2 types of illustration that we can produce after defining our network. Okay, so now once we have our architecture, we need to specify on how this architecture should learn from our training data. So right now what we have is a template of feature extraction, a blank template of those blank filters, as well as neural network. So now, in terms of compiling the network, there are 3 arguments that we need to provide to this program. So now, under the compilation, we will need the optimizers as well as the applications. And the 3 parameters that we need to specify here is the loss function, okay, optimizer, and also metrics. So in terms of loss function, there are 3 types of loss function for image classification. So the first type is categorical cross entropy, binary cross entropy, and also sparse categorical cross entropy. So the one that is most widely used is categorical cross entropy because we will be working on multi-class prediction most of the time. Okay, so this categorical cross entropy is the one that is suitable to generate the error term for multiple class prediction. The next one is binary cross entropy. This is only relevant for 2-class prediction problem. Sparse categorical entropy is a case when we want to try to tabulate the error in terms of probability instead of class. Okay? So the most widely used one is categorical cross entropy, and sparse entropy will be used in the case where we have a lot of categories to predict. Say, for example, more than 20 classes. Okay. So once we, okay, so now next is optimizer. What are the optimizers that are available? So the optimizers these are the 5 types of optimizers that are available. So there are more than that. Okay, but these 5 are the ones that is commonly used for an image classification. So the first one we have is Adam. The next one is RMS prop. We have stochastic gradient descent, we have momentum, and also NADM. So for image classification, stochastic gradient descent is always not recommended because it is a very stepwise learning, and it can be a little bit too slow when we are working on image data. So the ones that are recommended are Adam, RMS prop, and momentum, because it will adjust based on every single learning step that it is learning from. Yeah. So if you are interested, feel free to look into the mathematical algorithm behind. But for our level, we will know this at its highest level, where we want to know that whether they are stepwise or what kind of learning mechanism that it is taking. So finally, the metrics, we always specify an accuracy as our metrics for evaluation. So how good our CNN or architecture is will depend on how, the effectiveness between the combination of loss function and also optimizer. And in our case, because we mentioned that, okay, it's always recommended to use categorical cross entropy, and therefore the one that is left for optimize or optimization will be the learning rate. Okay, so this is a way of telling the network how you should learn. If you should learn fast or you should learn slow. Okay, that is on compiling. So now that we have defined the network, we have also specified how this network should learn. We can then take the combination of these two to learn from our training image. So in order to do that, we have to first define the batch size. So batch size here will be used in several cases, especially on the training step. So if this batch size indicates that, okay, every time we run the training, we will learn from 20 image at a time. Yeah. So that will define how many steps do we need for each training cycle. Yeah. So what do we need to feed a network? So in order to feed a network, we will need 3 things. So first is the network, which we have defined and compiled. The second thing that the network that we have defined and compiled is here, the model. Okay, so then we will need the training data set and the validation data set. Okay, so these are the 3 main components for fitting the network, and we'll see how each of this is coming together in later. So then another parameters that we need to specify is how many steps do we run for each cycle. So this epoch means cycle. How many times do we want this neural network to learn from our training image? Yeah. So the more time that the neural network sees our training data, the better it will learn. So it will reduce the error that it makes every time because of the forward and backward propagation mechanism. Okay, so that is epoch. Epoch of 100 means we want this neural network to see our training data for 100 times. And for each time it learns, give us the loss and also the accuracy. Okay, so steps per epoch is, So now we know that we want to run this machine learning, we want to run this training for 100 cycle. So for each cycle, how many little steps does it have to take? So now we know that we have a total of don't know how many training images, but we know our batch size. Let's say every time we are specifying this thing to learn from 20 images. So now what we need to do is to take the total training image divided by the batch size to get the steps per epoch. Yeah. So the steps per epoch means this run. Okay. And epoch means cycle. So as you run this code at home, it is going to take a while. It will take probably around 15 to 30 minutes. Less than an hour. Less than an hour for this case because this is a small case.
So that means code is running, do I have enough time to eat my dinner?
Huh?
If this code is running, do I have enough time to eat my dinner? Depends on what my dinner is. Too big dinners. It could probably be done, but if it's too short, you do it.
I will give you some indicators to help you decide. Okay, so now once you hit on this, it is not going to stop there without any output. So once you hit run, what it provides is the first line. So it will say that the first epoch is running and then whether it has completed 50 steps or not. Okay, so what we are trying to see here is this thing will keep on running slowly. And here it is telling us that the first step takes 20 seconds to run from my side. Okay, so the first cycle takes 20 seconds. The second cycle takes 13 seconds. The following cycle is about 13 to 16 seconds. Yeah, it will fluctuate as it goes. Yeah, so how long will this take depends on the learning rate that we specify. Yeah, we can take this as a baseline. Say this learning rate on 1000 image will take about 20 seconds. Yeah. So then it will also, once the first cycle is completed, it will provide us with the loss, which is the error that it makes. So what does this mean? So this line altogether means that the first time this architecture, this CNN architecture, extract the features and also learn the classification for the first time from our training image, it makes an error as high as 70%. And the accuracy of the first time is only 51%. Okay, so now this is on the training. So it will also run at the back end to try to apply these weights to the unseen data, which is the validation data. So it has run the validation, it has run this model over this validation data and tells us that, okay, the error that it makes on validation data is 68%, and the accuracy that it makes on the validation data is 50%. So now we know that this is as bad as flipping the coin, 50-50. Yeah, it is not so great for the first time. So now it will just keep on running the second time. So it will see the training data second time and then adjust the weights again. So once it adjusts the weights, what happens is we can see we should be expecting a reduction in the error. The error should keep on reducing from epoch to epoch, and the accuracy should increase from epoch to epoch. Okay, so at the end of 100 epoch, what we can see here is the loss function, the error now reduced to 40% from the original 70%, and the accuracy increased from 50% to 78%. So that is the best thing that this neural network is doing after 100 rounds of training. Okay. So now it is very difficult to read from this chart because it is very, very long. So what we can do is then we save this model, we save all the weights at this point of time as a H5 file. So this file will save the weights of all the single filters that it has learned this round based on this, this architecture and this set of images. So then we will be plotting some graphs to read these values. Yeah, because ultimately this value should help us to decide whether we should train the model a little bit further or should we stop, and how should we make a decision based on the graph. So if you look at this graph, the training accuracy is represented by the dots. The validation accuracy is represented by the line. So in this case, the training accuracy and validation accuracy, they are very close together. Yeah. And as we look at the loss graph, it is also similar. We can see that, oh, sorry, I forgot to mention, on the x-axis, these are the epoch. So from 0 to 100 epoch. And this one is the level of accuracy. In another chart, x-axis represent the epoch, and then this chart over here represent the error loss function. So we know that we started with 70% of loss and we keep on reducing. So based on this trend, we know that if we increase the training epoch further, this line may go further, maybe reduce further, right? And if we were to increase on more epoch, the accuracy can also increase, but at a lower rate. It seems to be plateau off at this level already. Yeah, so this is what we should read from here. So in these two graphs, based on the trend, we know that this model is not overfitting. It is fitting quite well. So if let's say we increase on the epoch, it will also increase its ability to make prediction. Okay, and we are not overtraining it. So what is a case to identify if a network has been overtrained or overfit? So we can look at this case. So over here we have one set of chart that represents the one that we have in the workbook. And if we see this trend on the right hand side, we know that this is an overtrained or overfit neural network. We should stop somewhere. So how can we identify them? So this chart is similar to this. So the training accuracy is identified by the dots, and then the validation accuracy is identified by the line. So what we can observe here is, as we train the model further, we are only training this architecture for 30 epochs. So we can see that the accuracy of on the training set keeps on increasing as we increase the time it sees the training data. But regardless of how this training accuracy improves, the accuracy on the validation set sort of plateau off at the 10th epoch. So at the 10th time, we know that the accuracy on the training is about 70%, and the accuracy on validation is about 70%. So as we train this neural network a little bit further, on our training side, it increases, but on the validation side, it doesn't increase further because we have already overtrained it. It has already been saturated. That is when we know if we want to stick with this architecture, we have to stop at the 10th epoch. Or we have to modify the architecture to make it a little bit more complex so that we reduce the overfitting. Okay. This is cvnlp. Okay, so a similar trend is observed on the error chart, error versus epoch chart. Do you understand this chart? Okay. And this will help us to decide what next step do we want to take. Okay. Okay. So now let's just say, go back to our case. Say we are good with this. We are good with this network. What we can do is then to use that to make prediction. So in order to make prediction, we will load the model which we saved earlier. So this H5 file to retrieve all the weights. And then we will do the same step to import the testing image data, and we'll use predict. We'll take the model weights to predict on the test image. So then we generate a class, some labels on the predicted labels, and then we will use the similar code to generate the same grid to tie with the predicted label. So now say, for example, the first image here, cat, is predicted correctly as cat. This cat is accidentally predicted as dog. And then the next one is predicted as cat, and so on and so forth. And we spot another wrongly labeled one, which is this cat predicted as dog. This is very quantitative. So how can we produce a more, this is very qualitative. How can we produce a more quantitative way of evaluating how good this predictive model, predictive power of this model? So now we will be using a classification report from scikit-learn to generate this report. So now we know that the accuracy of our model is 77%. Okay, so now the precision of this network in predicting cats is 72. Precision of dogs is 84, things like that. And we also generate a confusion matrix here. So now how do we read the information from here is that we have the true label on our y-axis and the predicted label on our x-axis. So now from this box, it tells us we have 500 cats images. We have 500 cats images, 400 of them is predicted correctly. 65 of the cats images are predicted wrongly. However, for the dogs images, we can see that there are 500 of them, 300 of them is predicted correctly, and 172 of them is accidentally predicted as cat. Yeah, this is how we should read the summary of how we decide the predictive power of the neural network is. Got it? Yeah. So now, as you go home and try running the code, feel free to adjust the stacking of the layers. Feel free to try to change the optimizers. But every time you change a certain thing, change one thing at a time so that you can trace the differences from one changes to another. Say, for example, once you change the learning step, what you want to observe is how fast is it learning from the epoch and the differences, the changes that it makes on this chart. Okay. At the same time, if this chart doesn't change that much, then you can go about to evaluate the differences in this accuracy and also this confusion matrix. Yeah. So only change a few things at one parameter at a time and see the changes. And when you see the changes, you should see the changes on the time it takes for each epoch and how the loss and accuracy evolve from epoch to epoch. And finally, whether it affects the predictive power of the neural network. Okay? Yeah? Awesome. Any other questions? I hope you learned something new.